Okie dokie. DIFC workbook. Physics. Electricity. Good. You okay, Siva? What's happening? You causing trouble? Oh, good. Right. Okay, RC circuits and graphs. Not too difficult today, this lesson. So imagine a capacitor is fully charged up, like in a flash camera, and then it's suddenly allowed to discharge in a resistor, like a light bulb. So, you know, an example might be like you have a light bulb, and then what happens is you have a capacitor here, and then you have a cell here, or maybe a battery, and then you have a little switch here. So when the switch is up like this, what happens? You get your current, goes around like that, and then this charges up. Okay. Then you press the button, and then what happens? The switch goes down, and then the charge that was in here is now released into the bulb. Okay. So usually in these diagrams we don't draw this part in. We just pretend it's been charged up, and then you turn it off, and then you have this. So the capacitor is discharging in the resistor. So we call this circuit that has one resistor and one capacitor, we call this an RC circuit. And let's add an ammeter to the picture. So let me stick in an ammeter here. Oh, sorry, here. We'll stick it in here. So let's put in an ammeter. Go away. Ah. Right. So I stick an ammeter in here. And let's measure what happens to the current. So what do you think will happen to the current? What will it be big? Will it be small? Will it be constant? Will it be increasing? Will it be decreasing? What will it be doing, do you think? Decreasing, yeah. It starts off with a lot of current and then reduces to zero. Okay. Here's an example of some data. So what I have here is the time, 10 seconds, and the current here in milliamps. So we go 100 milliamps, then 70, then 50, 35, and so on. It decreases here. I think what I would do, or what I want you to do, I want you to draw an RC circuit. So just put this as an example in your notebook, and then we'll stick in a little ammeter here, a milliammeter, and we'll put in a resistor. So that's an R, that's a C. And I would also like you to copy the table. So I want you to just copy this table as an example of some data that you might get from this, okay? So first just draw this, and then I want you to copy the table. So I'll put the table up when you're ready. got that? Can I go back to the table? Oh, no, not that. No, stop. I don't want you to do that. I want you to put this in. Put this in for table. Yeah. There.
Oh.
Yeah. You missed my, yeah, okay. Look, I put it in red or in C. No? Okay, did you copy that table down? Now, let's graph this data here. So what I'll do, I'll graph it. If you can read the numbers to me, I'll just put it in a graph here. So the time is in seconds, and the current is in milliamps. Is that right? What's the biggest current? It's like 70, is it? 100? 100. So we'll mark here as 100, okay? And the biggest time is 10?
Yeah.
Yeah. So we'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. And there's 50, and there's 75, and there's 25. Right, so what's the first current value? 100?
Yeah.
100 milliamps? Okay. Next?
70.
70, so that'll be about there. Next?
50.
50 will be there. Next?
35.
Okay, next.
25.
Okay, next.
17.
Okay, next.
12.
Okay.
8.8.
Yeah, next.
6.25.
Okay.
4.42.
Okay.
3.1.
Okay. So, what would you describe this graph as? Is it linear? No. What would you say it is? You've seen it in math class. Wow. Special name for it. No? No? Exponential. Exponential. Have you done this word? Yeah. You know, the graphs that look like this? Yeah. So, this here is, as you can see, this graph is exponentially decreasing. It's maybe not a surprise. So, what I want you to do, we will assume that the graph has this form, that the current is equal to some constant, I0, which represents the current at the beginning, times e to the power of minus t over some constant we call tau. This will make this type of graph. Now for this graph it's actually quite clear to see what the I0 is. What's the I0? 100. But what's not so clear is what's the constant here. Okay? We'll get to that in a moment. So I just want you to copy this down. Oh my goodness.
What? Decimal form?
Say again?
Decimal.
Yeah. I forgot to say that. Who knows what this letter is? No, believe it. No, it's like this, Siva. It's let me watch as I draw it. It's like this. What letter is that? Very good. Tau. Greek letter. Continue. This letter is called tau. Yeah, kind of like chow, you know. All right, continue. Can I continue, guys? Yep. Okay. So, yeah, what the heck is the 1 over tau? So, there's three like proofs on the exam, and this is one of the proofs. And the first proof is the UVATS equations, but I said that they've never asked that. So the second proof is this. The third proof is in the next semester. And the only other proof is, you remember when we did the box question with the particles in the box? I said, they don't ask you for that proof because it's too long, but they might test you on it. Okay. This proof isn't actually so hard. It should remind you of something you did in maths class. So we want to figure out how to calculate the constant I0. Or really we want to figure out, more importantly, how to calculate the tau. Okay. We don't like these graphs in physics. We don't like curved graphs in physics. We like nice straight graphs in physics. That's what we like. So let's see how we can draw that, or how we can deal with that. So if I say I equals I0 e minus t over tau, I can put a log on both sides. So now I get log I equals log I0 plus log e minus t over tau. That's one of the rules of logs. That log of AB equals log A plus log B. Next, maybe you can tell me, what can I do to this guy with the power here? Put it down, yeah. Now, who knows what log of e is? Natural log of e. 1. So now I get log I equals log I 0 minus t over tau, which I'm going to write like this. Log I equals minus 1 over tau t plus log I 0. Now suppose I was to make a graph, and on the graph here I put t and here I put log I. In this formula, log I is like y, isn't it? And what is the x like? If I look at this, what's the x? It's like t. So, what is this minus 1 over tau? Yeah, and this guy? It's like c. So in other words, if instead of plotting I, you plot the log of I, you'll actually get a graph that looks like this. An mx plus c graph. Okay? And you can figure out now that the slope of this graph, you can get the tau from it, because you can see that the slope equals minus 1 over tau. So therefore, here's our result. If you want to calculate the tau, that's equal to minus 1 over the slope. And that's if you graph this graph, where you put the log of I and time. Whereas in the graph I did earlier, I had I and time. But if you use log I and time, you get a straight line. And from the slope, you can get the tau. So this proof for this result is on the exam, as they've asked it a couple of times, and you realise it's a lot like what you did in maths class on the log lesson. Okay, so please write this down carefully into your notebook. Got that, folks? Not yet, no problem. Did you have maths today? You did at 9 o'clock. So what did you do today?
We did
Normal.
Normals and tangents.
Yeah.
And more optimization. Okie dokie, got that now? When, George,
Yeah.
you have, you sure?
Yeah.
Okay. Right, so, I've calculated already. This is the example we had at the beginning, right? I put in an extra column called the log of I, and here's the numbers here. 4.61, 4.26, 3.91, 3.57, so on. If I was to graph that, let's have a look at what you get. So there's the time in seconds, and there, here, let me, bum, 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 bum. What is this? Log of I in log of milliamps. Around we go. Okay. Right, so here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds, and it starts at 4.61. So I'll just go 1, 2, 3, 4, 5. So the first one here, 4.61, that would be, you know, like there. Then the next one is 4.26, that would be like there. And then the next one is 3.91, that would be like there. And actually what you'll discover is you'll get a straight line, and it gets down to 1.49 when it gets to 9, so it'd be like, you know, roughly something like that. That's what the graph looks like now. Okay. So the table you have earlier, you can extend it by adding in this row. So what I want you to do for me is to add in this row, and then once you've done that, you can make this graph in your notebook. I didn't have space, I don't think, to go to 10 seconds, is why it's cut out. But if you want to add in 10, just type in ln10 on the calculator. ln, whatever the number was actually. Got that? Yeah. And now the graph, please. Oh, that's you have this graph, Stephen? Yeah. Have you all dried out now? Have you dried out, or are you still wet? Your shoes are wet? No boots? No, this is the problem. Everybody has... Oh, Joe's shoes look okay for rain.
Yes, I think they're right.
Oh. What are you wearing for your shoes? You have sneakers as well, yeah. I like to get mine from Skechers, you know Skechers?
Skechers?
Are they? But they're not waterproof ones? I get the waterproof ones because, you know,
This one is waterproof.
yeah, it's better.
Yeah.
Okay. Continue? Continue? Yep. So, let's see. Anyways, we had this earlier, and when we put the logs on both sides, we ended up with this formula, which I mentioned earlier already. And I hope you wrote down the result. Did you write? Yeah, you wrote this down. The slope equals minus 1 over tau. You got that earlier, that's fine. Okay. What's interesting is not only the current, but if you were to replace the ammeter with a voltmeter, you get the exact same situation. So you know here with the current you can have the log, and you can do the same thing with the charge. The charge is also exponential, so you can do the same thing. You can do the same thing with the voltage as well. The voltage is also exponential. Okay, so in all three cases you could measure the current, the charge, the voltage. It all exponentially decreases. Okay. Now the point is everything is exponentially decreasing. The tau is called the time constant for everything, and the formula for it you have is minus 1 over the slope, but you have that already. But what you don't have is another formula for tau. In fact, not only is tau equal to this, but it turns out tau is also equal to the resistor multiplied by the capacitance, the resistance times capacitance. Now that's actually very useful to know, because it means that if you have the slope, then you can know the tau, the time constant. If you know the time constant, then if you have or, you can find C. Or if you have C, you can find or. So these two are useful formulas. So normally what happens in the exam, they'd ask you to make the graph. Then they ask you to get the slope. Then they might say, if the resistor is 50 ohms, then what is the capacitor? And so you can use this to get the capacitor. So did you write that formula down? Okay, and there's one last interesting thing. You have that, Chow? Mm-hmm. Yeah? They're all the same, except it's just Q instead of V and so on. If I go back to this graph here, now, when will this graph reach zero current? Well, technically it doesn't, because it's an exponential, which you probably learned in math class. It doesn't actually reach the x-axis. But of course, that's not realistic, right? In real life, the capacitor will eventually run out of charge. So this graph is only accurate for a small time, because what happens in real life is this. The graph decreases exponentially and then hits the axis and stays flat. So the question is, what is this discharge time? How long until you go from current to no current? And the answer is roughly 5 time constants. That the time to discharge is roughly 5 multiplied by the time constant. Now it's only approximation, but this is what they used in the exam. And of course there's no surprise then that the units for tau must be seconds, because it would only make sense if it was seconds. Sorry, I realise you're trying to write this down, but I just want to open up a program here. Okay, you have that? Yep. We're good? Do you have it, Shell?
Yeah.
Okay.
Yeah.
So let's have a look. We have a question here. The current discharging from capacitors measured every 10 milliseconds. The table below shows the data. So you have current in milliamps and time in milliseconds. Graph this in an appropriate manner. Right, so let me just copy this down here. Time in milliseconds and current in milliamps. Oh, don't do that. Okay. Right, it goes from 0. So you can copy this with me. 0 plus 10 up until 100 milliseconds. Up until 100 milliseconds. Okay. Next, the current. So what's it? 1000, 841, 707, 595, 500, 420, 354, 297, 250, 210, 177. Okay. And let's just pop that there. That's all fine. Right. Now, graph this in an appropriate manner. So you might think, oh, easy. Time, current. No, that's not the graph we make. What graph do we make here? Time and log the current, okay? So what I need to do now is make another column. And this is the log of the current, and the units are log of milliamp. Okay? So if I just do a good old ln of that, here it is here. Okay, so far? So I don't really care about this anymore, because I use this for my graph. So what I'll do, I'll just copy, paste special, I just want the, let me delete this now, delete columns, there we go. So now I have the two things I want. Right, make my graph. So let's put in the graph. So what type of graph should I get now? Should be linear. Going up or going down? Down. So let's scatter. This is just example graph. Time in milliseconds. Log of current in log of milliamps. And there, well, assume. Okay, there we go. Right, there's our graph. Will we add the line to the graph as well? Oh, come on, dudes. Wait, no. How do, oh yeah, okay, here we go, here. Insert line. Oh no, I had it, sorry. Okay, so there is my example graph there, going straight down. Right, how do I estimate the time constant? What do I do? -1 over the slope. So I need to estimate the slope here. Now it's kind of hard for me to see because the numbers are quite small. So it's this number divided by the base. Sorry, can you see there? That, actually I wonder, can I copy this into here? Can I copy this? Copy, paint, edit, paste. Do you see paste? Where's paste? Can anybody see paste? I'm looking for paste. Okay, I can't. Right, so if you can look closely, what would you say the height is here? About 5 to 8? About 3 units? About 2, is it? Oh, that's a 7, sorry, 5 to 7, so about 2 units. And then the base is 100. So you can calculate on graph paper. Now I don't have graph paper, so I asked Excel to do it. So you can see Excel has worked out the slope here for me. Can you see that? The slope is minus 0.017x plus c. So Excel has said that the m is roughly minus 0.017. Okay, so then what's the tau? The tau then is roughly minus 1 over minus 0.017. So can someone just type that in? What's that now? 58.82. Ah, but what's the units? No, not seconds. Because look back at the question. Why am I saying not seconds? What do we have on the x-axis? What unit? Milliseconds. Not seconds, milliseconds. So this here is milliseconds. Okay, now, to be careful with that. Alright, next. How long until the capacitor fully discharges? So how long is that? 5 tau constants. So can you multiply that by 5 and let's see what we get. 294. Okay, milliseconds. Okay, and finally D. What was the value of the resistor? And you know the capacitor is 200 millifarads. So you can use the formula tau equals RC. Now you have to be really, really careful because we're messing around with units here. Tau is milliseconds, but it really should be seconds. Because here, what unit will we use for R? Ohms. And C is capacitor, so farads. Okay? So, you know, if we want to stick to using ohms and farads, then this guy should be in seconds. So if I convert this into seconds, what would that be? 0.058. And that should equal R, which we don't know, and C, which I put into farads, is 0.2. Yeah. Now I actually could leave this as millifarads, and then the millis would cancel, but then that's getting really messy. So the R will be 0.058 divided by 0.2. So what's that, please? 0.29 ohms, is it? Yeah? Is that okay? Now, you have to be careful here with the units, because I really tried to annoy you by putting in milliseconds and milliamps. Now, what's really, really interesting is it actually doesn't matter about the milliamps here. You might be thinking, well, what about the milliamps? Does that mean these are milliohms and millifarads? In fact, it really doesn't matter about the milliamps, and let me show you why. So look at this graph here. Let me call this one x and this one log y. And I want to calculate the slope here. So here this is, you know, x1 log y1, and here this is x2 log y2. What's the slope from math class? It would be log y2 minus log y1 over x2 minus x1. Now what's the units here? Well, that'd be the units on the top divided by the units on the bottom. Okay, so in this example, what's the units for x in this example? Milliseconds. Now what about on the top? Look what happens here. You can change log y2 minus log y1 into log y2 over y1. What's the units for Y2? It'd be amps, milliamps, and the units for Y1, milliamps. But Y2 over Y1, what units is that? No units. No units. So you could actually change these to milliamps, microamps, gigaamps, and you'll get the same answer. Because when you calculate the slope, the only unit that matters is the time unit, which affects the units you use for time. Okay, that's kind of hard. The short story is, it's really only this unit that matters the most in your calculation. This actually has little effect. It has no effect on the slope. So just be careful. If you're using milliseconds here, then this is also milliseconds. Okay. So really for this lesson, it's like what we did yesterday. We're just making graphs and we're using our graphs. So I think I just give you 2 questions, isn't it? Or 3 questions. Yeah. But that's not really time to do it now. So before you go, Friday, we have a double class. Now the next lesson I need 2 hours to cover. So it means we can do our tutorial on Monday. But if you like, we'll do a double tutorial on Monday, because there's a lot we've done in electricity and Friday's class will be a little bit hard. So we'll do a double tutorial on Monday. Also, there'll be a new student joining us on Monday for exactly 1 class and 1 class only. Do you know Tiago? Yeah. So there's a thing at the school at the moment where the principal would like teachers to work with the non-teachers, a day in the life, and the non-teachers to see what the teachers do. So I partnered with Tiago, so he's going to sit in and have a look at what a physics class looks like, and then I'm going to talk to him about what he does, and it'll all be great. So he'll be joining us on Friday. So just pretend he's not there. He's only wanting to see what a physics class looks like. And of course you can talk to him if you want to. Act normally. Don't act any differently, okay?